and welcome to the third video I'm going to be doing on threat taxonomy. So in this video, I'm going to consider specifically what malware authors do, what techniques they apply to achieve resiliency. That is, what do they do to make themselves hard to get out the system, maybe even hard to detect by anti-malware vendors. So if you recall from the first two videos, the first dimension that I talked about was the way the threats propagated. The second dimension was talking about the kind of harm that threats might do. And in this video, we'll do the third dimension, which is resiliency. So the most common technique that I've seen for that malware authors use to stay resilient is something called polymorphism. Polymorphism. And the idea behind polymorphism is that a piece of malware rather, will try to encrypt itself or encrypt large chunks of itself and then basically decrypt itself on the fly as it's being executed. So for example, imagine you've got a file. Let's say this is a Trojan, which is a piece of malware. What'll happen is maybe there'll be a section of code. Let's imagine this. This is not how it's going to happen in real life, but I'll give you an example. Let's say the main body of the code right here will be encrypted. So let's say we'll imagine that nobody can actually read it. It looks like complete garbage. And then somewhere at the maybe when the malware starts, there'll be a jump instruction which takes the. So rather than kind of executing the code sequentially, there'll be a jump instruction which tells the computer to start looking here for code to look at this piece of software. And then the malware will contain here a decryption routine. So there'll be a decryption routine right here. Decryption routine. And this decryption routine will give instructions for how to decrypt this part of the payload. So maybe after the decryption routine is executed, maybe this part will be now decrypted and will actually now look like legitimate code. And then after the code here is decrypted, the transfer is put back at the beginning of the now newly decrypted code segment, and then the code's basically executed from this point onward. The idea here is that because encryption is being used, it's very hard for anti-malware technology to figure out what this code actually does because it was encrypted prior to its being decrypted by the decryption routine. And moreover, you could actually design malware, or design techniques for doing polymorphism in which you use a different decryption key, let's say, or maybe even a slightly different decryption routine for each invocation of the malware. So in other words, you might see malware where underneath you might have the same copy. You might have like 5 copies of the same piece of malware, but one of those copies might be, or maybe each of those 5 copies are decrypted or encrypted rather, somewhat differently. So maybe this one is encrypted, this way, and this one is encrypted this way, and maybe this one's encrypted this way, etc. And maybe this one's encrypted in some other way. I'm just kind of drawing different ways you can imagine encryption, or visualize encryption. And because they're encrypted in different ways on the outside, or rather ostensibly they look different, but underneath they really are the same. And as you can imagine, this is a very powerful technique that malware authors use for being able to effectively detect or evade detection by anti-malware vendors. Now, another technique that a lot of the bad guys use is something called metamorphism, and you see a lot of morphisms here, but metamorphism. And metamorphism is kind of related to polymorphism. Again, it's an idea of changing something. That's why the term morph is being used. And what we're going to be doing in metamorphism is, this is where a malware author will make superficial code changes. So if polymorphism is about encryption of the code, metamorphism is effectively just making changes to the code, but changes that don't really affect materially what the code does, but actually just make it so that it looks just different enough to evade what a malware or anti-malware vendor might be trying to do in terms of detecting it. So for example, you might talk about inserting no-ops or no operations, or things that don't actually do anything into the code. You could reverse instructions, reverse branch conditions, swap registers, modify the order of subroutines. You can swap a small piece of code for another small piece of code that's a bit different but does the same things. It's the original, and so on and so forth. And actually, let me do an example so you can kind of get a better sense. Imagine, and this is, I'll do a little bit of assembly language, but it'll be hopefully straightforward, even if you don't know assembly. So maybe you'll have an assembly language instruction of the form move ax comma 5, which basically says to move the value 5 into the register ax. And you might see a piece of malware with this instruction on it. Now, what we can do is, you can imagine that there is another way to implement this. What I can do, instead of moving 5 into AX, I can move 3 into AX. So move AX comma 3. and then I can add 2 to AX. Okay, now the result in both cases is that AX will ultimately have the value 5 in it. In the first case, we just put 5 in directly. In the second case, we put 3 in, then added 2 more to get 5. Okay, and these two pieces of code do the exact same thing. They have the exact same functionality, but they look different. And so as a result, if you try to look for whether or not this piece of code matches a particular threat type or a threat that you know about, if the malware author goes ahead and makes these minor modifications, even though the underlying threat is doing the same kinds of things, because it looks a little bit different, it might evade detection. Obviously, we're not going to just be looking for a couple of different or minor code changes, but malware authors in general are going to be trying to make many, many such metamorphic changes. And then in the context of polymorphism and metamorphism, one term that you'll hear quite often is something called a packer. And a packer basically is a tool that takes an existing piece of malware and it applies techniques like polymorphism and metamorphism and compression and so on, and at the end gives you kind of a self-contained package that contains the malware in it. So basically, packers use metamorphism, they use polymorphism, but they are kind of ready-made packages for doing these sorts of things. Now, what's interesting with packers is that their roots are actually in legitimate software. In fact, people used to apply packers in practice to do things like save hard drive space. So back when that used to matter a lot more, and certainly there was a time where hard drive space was a premium. So you might write a packer to compress your file, and so that would save hard drive space, and maybe make the file more compact for transmission. Another reason you might want to pack something legitimately is to avoid piracy. So for example, a lot of software vendors were concerned about people pirating their software, so they went ahead and created packers that would obfuscate their software and make it difficult to pirate, and make it difficult to kind of circumvent any copyright mechanisms and so on. And that was a legitimate use for packers, but nowadays malware authors or malware writers use packers extensively themselves to evade detection, or to rather help evade detection. And I think it's probably one of the most common techniques used in malware. So you will see many, many malware samples rather that are packed, and so this is a very common thing to see. Aside from kind of hiding the contents of the file, malware authors can go one step further and try to actually hide the file on the system itself, rather hide the presence of that file on the system. And the technique that or the term that's used to describe that set of techniques is rootkit. You'll often see the term rootkit, and a rootkit basically is a piece of software that tries to hide its own presence, and it does so by doing things like intercepting system calls and returning back false answers and so on and so forth. So for example, imagine you've got a computer system here, and there's maybe a lower level. Now what will happen is the way the operating system works, let's say you want to do something like a directory listing. You want to see all the files on a particular directory, and you might imagine like Windows Explorer doing this sort of thing, and so on and so forth. So what actually happens underneath is that in terms of the actual system itself, the operating system, there'll be a call issued that says, okay, tell me all the files that are on the system, and then there'll be a kind of a response back from the operating system saying, okay, here are all the files. So when you want to do a directory listing, or you want to list all the running processes, there's a system call followed by a response underneath. And what a rootkit will do, or what some rootkits will do, is they will try to interfere with the system call. So they'll intercept this system call, so they'll find a way to intercept it. This is maybe what the rootkit is doing. Okay, so the rootkit's right here. It'll interfere with the system call, intercept it, and then modify it. So for example, let's say that the system call said, give me a list of all the running processes, or give me a list of all the files in the file system in a particular directory. The rootkit will find, and typically there'll be a list of files. It'll be file 1, file 2, etc. And maybe somewhere in here there's the rootkit is listed among the files. And then maybe there'll be some more files that if you were to just do an actual listing, you might see these files in the rootkit will be one of them. Well, what the rootkit will do is it'll look for the system call, and this response goes back to the operating system up here, and the rootkit will basically find itself on the list and just remove itself from the list. So maybe it'll go ahead and say, okay, well, I don't want anyone to find me, so I'm going to go ahead and just remove myself from the list. I'm going to edit the list, take myself off of it. And so now anybody seeing or doing a file listing is not going to see the rootkit there listed among the files. But even though the rootkit is still on the system itself, it's running there nefariously, but it's kind of hiding its own presence. It's kind of putting on like an invisibility cloak, if you will. So it's still there, but no one can see it easily. And that's, it's a very powerful technique, and we definitely do see a lot of rootkits in practice, and they're very difficult to get rid of because they're good at kind of masking their own presence. Although there are techniques for being able to detect rootkits, and maybe I'll talk about rootkits in more detail in a future video, but for now I'll kind of leave it at that. And then the final thing I do want to mention in terms of techniques for resiliency are what we call kind of turning off AV. So one of the first things, or turning off anti-malware, turning off AV. And remember I talked earlier about how people say antivirus when they really mean anti-malware and vice versa, and I actually made that mistake just now. But really when we talk about antivirus, we typically mean anti-malware in general. So imagine just turning off any of this software. And in fact, what malware might try to do is the first thing that a piece of malware will do when it gets on a system is it'll try to get rid of or block any anti-malware software you've got running from doing any work on that file subsequent to that. So for example, one of the most common things a piece of malware will do is it'll find what's called the hosts file on the system. So there's often a file on a system called the hosts file. And the host file, for most systems, it's actually empty, but what the host file can be used to do is it can be used to map domain names to IP addresses. So for example, on the internet, most actual systems can be addressed by this numeric address, which is called the IP address, and it's just some number like 192.168.1.7 or something. Actually, that's an internal IP. You can have external IPs as well. And typically, what happens is that you don't remember IP addresses. You might remember a domain name. So you might go to like www.website.com or examplewebsite.com, and what's happening underneath is that domain name is being translated into a numeric address, which is how your computer really knows how to find that destination. In much the same way that when you dial a telephone number, let's say you're using your cell phone, you might hit a name in your contact book. That name in the contact book will get translated into a phone number, which is then how the telephone company knows how to find that phone. It finds it on the basis of the phone number. And so a lot of antivirus software, anti-malware software needs to do things like periodic updates and fetch new definitions and new signatures and so on and so forth. And it turns out that if you can put an entry in it, if you can put an entry in the host file that says, instead of going to, let's say there's a domain for like vendor.com in here, or even if there wasn't one, maybe you can add an entry to it. A lot of malware will go ahead and modify the entry for vendor.com and say instead of going to a legitimate IP address, they'll put a fake IP or an IP that goes to some malware server. So some kind of bad IP address will be put in there. And the idea is that with that bad IP address in there, the malware or the anti-malware software rather will not be able to find the actual legitimate vendor, but they'll be kind of stuck going to some fake vendor or some non-existent site, and you won't be able to get updates, and the malware will effectively not be able to stay on that system indefinitely until you can maybe manually update or update in some other way. Now, I'd say that the most amusing case I've ever seen, I've seen an instance where a malware actually patched a vulnerable system and then installed more anti-malware software on the system. And now you might be wondering why they're doing that, and I'll get to that in a moment. Now, what it did is it took a legitimate piece of anti-malware software. The malware installed this anti-malware software on the system. It actually modified that software subsequently so that the anti-malware software signatures database did not detect the malware that installed it. And the reason that this kind of odd behavior occurred, the reason that malware would engage in such seemingly bizarre or erratic behavior is territorial. Once a piece of malware invades your system, it doesn't want other pieces of malware from other malware authors to gain access to that system. And so it might actually go ahead and protect certain parts of the system so that it has sole authority over that system and doesn't have to worry about anybody else kind of invading its territory. So I thought that was pretty amusing, and I've seen that happen a number of times as well. And so to wrap up, I do want to emphasize that most threats today, that they actually are blended. So they may adopt many of these attributes. So for example, you can have a packed Trojan that contains exploit code which creates a backdoor on the system and then acts as a downloader that in turn downloads something that disables AV software. And so or anti-malware software. And so the reality is that you may have very complex threats that blend many of these different attributes.